Alrighty. So I'm starting this new thing here. I'm gonna be having some few lessons on the channel, mathematics lessons, or one can say some mini lectures on some concepts of mathematics, and this might help some of you out there. And I'm doing this selfishly. This will be some of, I won't do everything, but I'll just do some of the concepts that I like and some of the concepts that actually I perceive people to be struggling with in first year mathematics. So today we're going to be starting with limits. I always hear people saying that, I've reached my limit, but here we're going to be talking about limits from a maths perspective. So in mathematics, notation is very much important. So maybe you might have seen, or if you're dealing with limits, probably the notation that you must be familiar with is this. So let's say I say lim x f of x, let's say equals to L. So these are just variables. Limit of f of x as x tends to a. So this thing reads as follows. So when we have this, because it's important for you to understand this, when we have this, we mean that the limit of f of x as x tends to a is L, right? In other words, f of x tends to L as x tends to a. So this is what actually this notation, this is how we read this notation. So I'm just going to put it again here because I think this is very much important for people to note, or for students to note that. So if I write this, I'm going to write it again. If I write this equals to L, what we are saying is that f of x, tends to L as x tends to a. So this, notation here is, we say that f of x tends to L, and this notation here means x tends to a. Now, this is very much important to note from a theoretical perspective, because I think what I've realized, especially for first year students who have done limits from high school, they think that when we say x tends to a, that means x equals to a, and that's not necessarily true. So x tends to a and x equals to a are not the same thing. They are not the same thing. They are not. So when we say x tends to a, what's happening here? So when we say x tends to a, what we mean is that x gets closer and closer to a. That's what we mean. So obviously, if you want to evaluate this this limit here, we evaluate it based on what x tends to. And I'm gonna do maybe an example just to actually show you what I mean by that. So when we say x tends to a like this, what we mean is that x gets closer and closer to a. One of the things that actually made me to understand limits better was real analysis, because in real analysis, if you look at the definition of what a limit is, it really gives you that in context. I mean, the definition is quite very clear there. But in any case, so let's say, for instance, we say that you must find the limit as x tends to, let's say, 2 of x squared. What is the limit of this? So one could say, okay, the limit of this is 4, right? And then the question would be, how did you get 4? How is the limit of x squared 4? Now, someone can say, isn't it that the limit of x tends to 2 of x squared is 2 squared, which is equals to 4? And they are right. You know, you can look at it like this. So if you look at it like this, it looks like we have substituted x to be equals to 2, and then if we substitute x equals to 2, then we have 2 squared, which is 4. This is the problem, I think, that makes students to think that each time I take the limit, I must just substitute. And if I substitute into the function or the expression that I'm given, in this case x squared, if I substitute x to be equals to 2, then I'll get 4. Then students think that, oh, each time I have a limit, then all I have to do is just to substitute the value. So, but now suppose then that you have the limit as x tends to, let's say, 0 of 1 over x squared. Are you going to substitute again here? Are you going to say that this is equals to 1 over 0 squared, right? Which is undefined if you do this. So you can't do this. This is wrong. And now this actually brings us to what we actually mean when we talk about a limit. So when we say, I'm going to go back to this example of the limit of as x tends to 2 of x squared. When we say that, when we talk about this limit, what we're saying is that we want to look at x squared, right? So in other words, the values of x squared when x gets closer to 2. In other words, what happens to x squared as x tends to 2? In other words, as x gets closer and closer to 2. So if you were, let's say you had a table and say you had some values of x and you have x squared here. Let's say we choose some values of x. Maybe we have values like, let's choose values which are closer to 2 but not 2. From the left of 2, maybe let's say we have from the left of 2 to be 1,9, and then you have maybe 1,99 and so forth, and then you have, let's say on the right of 2 we can have 2,01, 2,001, etc, etc. Let's say we pick values which are very closer to 2. Well, I don't have a calculator with me right now, so I cannot evaluate these numbers. But if you do that, maybe if you do this with your calculator right now and you put numbers like you put 1.9 squared, you put 1.99 squared, 2,01 squared, 2,001 squared, you would actually realize that those numbers, or whatever numbers we're gonna have here, those numbers will be closer to 4, right? Maybe you'll get like maybe 4,0 something, or maybe 3,98 something and stuff like that. So, but it will be numbers which are closer to 4, and that's why then in this analogy, the limit as x tends to 2 of x squared is actually 4, right? It is actually 4. But then I'm gonna come to the point of when do we substitute and why do we actually substitute, because at the very same breath, right? Did I say breath? But in the same token, let me just set another page. In the very same token, like for the other example, this example of the limit as x tends to 0 of 1 over x squared. Another student can look at this and say that, no, the limit is undefined. Why are you saying the limit is undefined? And they'd be like, no, when you substitute x to be 0 here, you're going to have 1 over 0 squared, which is 1 over 0. And we know that when you divide by 0, it's undefined. But that's not the approach to look at a limit. I'm going to tell you, when do you substitute? And then when do you not substitute? In this case, you cannot substitute x to be equal to 0. If you do that, then that's when you're going to say that the limit doesn't exist. But then what do you do in this case? Again, like I said, the concept of a limit is to say that you are actually, when we say x tends to 0 in this case, what we're saying is that x is some numbers, or is a number which gets closer and closer to 0, but not 0. So if we do that here, I'm not going to make a table, but you can think about this perhaps algebraically, or let's analyze this together. So if x becomes a number that is closer to 0 but not 0, so let's say that x is 0, 1 or x is 0, 001, but basically x is becoming smaller and smaller and smaller. What happens to this fraction, 1 over x squared, is that it gets bigger and bigger and bigger. We know in mathematics that if you actually divide with a smaller and smaller and smaller number, what happens is that the fraction becomes bigger and bigger and bigger. So that's how you need to think about it here. What we need to think about here is that, x gets smaller. What happens when x gets smaller? 1 over x squared gets bigger, right? So therefore, in this case, that's why we say that the limit of 1 over x squared is actually infinity. We're going to talk about a bit later here about the left limit and the right limit, and then how those two relate and stuff like that. So in a nutshell, that's what a limit is. When you're taking a limit of a function, what you are actually trying to do here is that you're trying to evaluate that function when x, if you're dealing with the variable x, when x gets closer and closer to that number. So I just want to put it clear here, that the limit as x tends to a of f of x, if that is equals to L, then what that means is that so what this means is that f of x gets closer to L as x gets closer to a. Or you can say f of x tends to L as x tends to a. I think I'm repeating this again, but for good purposes. So f of x tends to a as x tends, no, f of x tends to L as x tends to a. Right? So I think with those two examples I've shown that we do not necessarily it is not always the case that you must substitute. But please bear that in mind. I'm going to come to that question of when do you substitute and when do you not substitute. But I wanted us for a second to understand what we mean by limit. Because if we understand that, then it will be easier for us to deal with whether it's examples and stuff like that. So now, okay, I wanted to say, I wanted to give this example here to say, and I don't know how will this land on you, but when someone says, for instance, they're like, the limit for my groceries, right? Maybe someone is saying that the limit for their groceries, let's say they say is 1,000 rand, right? It can be that, let's say this person had a budget which is greater than 1,000. So maybe they had a budget which is, let's say their budget is 1,200, right? And then they say that their limit is 1,000. What they mean actually in most cases is that they don't actually spend 1,000 on the dot. So maybe they can spend, I don't know, maybe 951 47 cents, then they'll still be fine, or maybe they spend 1,002 52 cents, they'll still be fine. Or maybe they spend I don't know, let's say 1,000 and 101 cent. So usually the person will be fine with this, or most people will be fine with this, especially if their budget is 1,200. I'm just giving an example here. Usually that's what happens to a lot of us. When we say our limit is this much, we actually mean that, if the number is, at least closer to that limit, then we are still fine. So all these numbers here are still, all of them are closer to 1,000, So all of these numbers, if we represent this, whatever the person has spent here as X, so let's represent by, let X represent, spending. So we can see here that X tends to 1,000, right? So in other words, X is not 1,000, but X is, some number closer to 1,000. And usually we are fine with that. I'm just putting this narrative here to just give you, or to solidify, when was the last time I heard the word solidify? To solidify or to validate, this concept of limits, of what we actually mean when we talk about a limit. So now there is something that we call the left limit and the right limit. Maybe let's get into that just now. So we have the left and the right limit. So the left limit, we use this notation, and the right limit would use this notation. So now if I write like this, what I mean that is that we're looking for the limit of f of x, but as x tends to a from the left. So this here, or maybe let me just say x tends to a from the left. Sorry, why am I putting a minus there? Okay, so the minus, it means that x tends to a from the left, so from the left of a, and then x tends to a positive will mean that x tends to a from the right of a. So for instance, let's say that this is a, right, on the number line. So a is some number, so obviously you can approach a from the right of a or from the left of a. So if you're approaching it from the right of a, this side here, it will be x tends to a from the right, and this side here will be x tends to a from the left. You're approaching it from the left. For example, if a is 2, then x tends to 2 from the right. Now here we're approaching 2 from the right of 2, so meaning that here we're talking about numbers like 2,01 or maybe 2,001, but these are numbers which are closer to 2 but from the right of 2. And then this will be x tends to 2 from the left, and then if we do that, maybe we're talking about the number 1,9 or 1,999, stuff like that. So where does this get us to, right? So let's say, for instance, let's go back to our example of the limit as x tends to 2. Let's say we want to find the limit as x tends to 2 from the left of 2 of x squared. So if we do this, what we mean is that we're picking numbers closer to 2 but from the left of 2. So maybe it can be 1,9, it can be 1,99 or 1,999 if you're using this as your progression. So you'll also see that whatever values you pick here, those values will also be closer to 4. I don't have a calculator with me, but the values will be actually closer to 4. So, but these values here will be closer to 4. So for instance, I think it would be better if we draw the parabola. So this is the parabola. Sorry, but you know that it goes through the origin, right? I'm not drawing up to scale here, so it must go through the origin. So let's say this is 2, and then we know that if this is 2, this will be 4. So now you can see that obviously if you're approaching 2 from the left of 2, then the values of y will also be closer to 4 but from the left, from below 4. They will also be below 4, so it will be values that are actually below 4 but closer to 4. So then in that case also we then have that the limit as x tends to 2 from the left of x squared is 4, right? You can check this with a calculator. You'd see that the number also tends to 4. But then let's say that we now want to check the limit as x tends to 2 from the right of x squared. So now from the right, we're coming from this side. So obviously you see that if you're coming from the right of 2, so that is, you are talking about values like 2,01, 2,001, and 2,0001, etc., etc., if you use this as your progression. So we're talking about values which are actually closer and closer to 2, but from the right of 2. And you can see also from the diagram here that if you do that, so this will be getting closer to this value. So this will be values which are above 4 but closer to 4. So this will be your 4,01s, etc., etc. So this will also be 4, right, from the diagram. So what are you noticing here? You are seeing that the limit as x tends to 2 from the right is 4, and when x tends to 2 from the left is also 4, right? So actually we have a rule on this. It's actually a theorem. So in that case, if we have this, it means that the limit as x tends to 2 of x squared is actually indeed 4, like we have seen before. So we have a theorem on this, and the theorem is that if the limit as x tends to a from the left of f of x is equals to L, and the limit of x tends to a from f of x is also equals to L, right? So that is actually the limit as x tends to a from the left of f of x is equals to the limit as x tends to a from the right of f of x, and they are all equals to L. Then it means that the limit as x tends to a of f of x must also be L. So in other words, for the limit to exist at a point, it means that the left limit and the right limit must be equal. And then whatever that they're equals to, then that is actually what the limit equals to. Like we have seen in our case here, that if we have that the limit as x tends to 2 of x squared is 4, what this means is that the right limit is also equals to 4, and also the left limit must also be equals to 4. Otherwise, then the limit doesn't exist. For example, let's do an example on this. For example, let's check this out. Let's say you have the limit as x tends to 0 of 1 over x. Does this limit exist? Let's check. So for us to check, let's check the left limit first. So let's check the left limit. So what happens if we approach 0 from the left, right? So it means that we are looking at numbers which are closer to 0 but from the left of 0. So this is numbers like negative 0,1, negative. So let's say maybe we take, this is x, say we have minus 0,1, minus 0,01, minus 0,001, right? And then now we have 1 over x here. So 0,1 is 1 over 10, so this will be minus 10. This will be minus 100. This will be minus 1,000. So what do you see here? So you see that we see that when we approach 0 from the left, the numbers become negatively big. Is that even right to say negatively big? But you can see that the numbers are becoming bigger but on the negative side. So this is minus infinity, right? It's a no-brainer. You can also analyze this just from the just from the fraction itself, that when x becomes, smaller, when x becomes bigger, but when x becomes smaller, yes, in the negatives, 1 over x becomes bigger in the negatives. Wait, that is very wrong to say, right? Because in the negative side, there is nothing as is becoming bigger in the negative. It is becoming smaller. Hey, you get what I mean, right? In any case. So similarly, you can also see that if we do the same for 1 over x, but from the positives, let's say we have x here, and instead we choose to have numbers which are approaching 0, but from the right of 0. I hope this makes sense, guys, because let's say we have 0 here. So if we're approaching, so this side here, when we approach 0 from the right, so this is x approaching 0 from the right, and when we're approaching 0 from the left, this is x approaching 0 from the left. So if we then do this for this, so if we're approaching it from the right, that is from the right of 0, so we're talking about positive numbers which are closer to 0, so it can be 0, 0,1, 0, 0,01, or 0, 0,001, etc., etc., depending on how. It's not like you have to always put them like this. You can pick any numbers. In fact, when you get advanced in this, you don't even have to do this types of tables. You just have to actually, evaluate the limit that you're taking, and from just using the algebraic tools that you have to say, oh, if x is becoming smaller and smaller, but from the positives, what is 1 over x? So this is going to be 10, this is going to be 100, this is going to be 1000, right? So you can see, or we can see, that the limit as x tends to 0 from the right of 1 over x is actually infinity, right? So what it means then here is that we have two results, is that the limit as x tends to 0 from the left of 1 over x is minus infinity, and the limit as x tends to 0 from the right of 1 over x is infinity. So the left limit, in other words, is not equals to the right limit. So therefore, in that case, the limit as x tends to 0 of 1 over x doesn't exist, right? And in fact, if you know this very well, you would know that this is true because this is the hyperbola. 1 over x is the hyperbola, and then if you have 1 over x, we know that x equals to 0 is the asymptote. So the limit doesn't exist, obviously, at the asymptote, and we actually have this. So here is another important, this is important. This theorem here is actually very much important for limits, that the left limit and the right limit must actually be equal for the limit to exist. If the two limits are not equal, then the limit doesn't exist. So you actually see this with either you're having an asymptote on that point. That's where you are most likely to not get the limit to exist. In other words, you don't have the left limit and the right limit being equal. The other thing is also with the other point where we do have, or where we can have that the left limit and the right limit don't exist, is actually when you have something called a piecewise function. So a piecewise function will be maybe something like this. Let's say you have f of x equals to, let's say is equals to x squared, maybe between 0 and 2, and then maybe is equals to x from when x is greater than 2. So if you are to plot this kind of function, let's say this is 2. So it means, what it means is that a piecewise function is a function that is made up of pieces of other functions. So between 0 and 2 we have a parabola, So let's say this is the parabola between 0 and 2, and let's say from x is greater than 2 we have the linear graph x, so meaning that then we have, maybe this is the graph. So this is how the graph will look like, and we don't include 2 here, and let's say here we do include 2, and then these are included points. So if you have done piecewise functions, then you will have something like this. So you can see that here we have a jump, or we have a discontinuity here. So the graph is discontinuous here. So here we have a discontinuity. So now, because of this discontinuity, then here the limits won't be equal. The left limit and the right limit won't be equal. Like for example here, if we take the limit as x tends to 2 from the left of f of x, if we're coming from the left of f of x, then we are actually analyzing it using the graph x squared, because and if we do that, we'll just see that this will be 4 if you look at the graph. And then if we take it from the right of f of x, so from the right we're coming here, so we'll actually be using the linear graph, and then so this is 4, this here will be 2, and this will be 2. So you can see that the left and the right limit are not the same, so therefore the limit as x tends to 2 of f of x doesn't exist, right? So that's that. So yeah, the concept of piecewise functions, yeah, I just hope that maybe people have learned it, or you have learned it. But that's usually where you actually can have the limit not existing, is that either maybe in this case where you have an asymptote, or perhaps in a case where you have a discontinuity. That's when you can have the limit not existing, right? So here's another important thing to note, right? I mean, that's the other important thing to note. So far we have learned that when we take the limit, I mean, so far I think that what we have learned importantly is this theory here, which is actually very much important in limits. And also the other thing is also that what I've covered before about what do we mean when we say that you're taking the limit as x tends to a. That is, x is not equals to a, but x is a number that gets closer to a. So when do we substitute, right? Like, when do we say that the limit as x tends to 2 of x squared is 2 squared, which is equals to 4? Because here we seemingly have substituted x equals to 2, or it looks like we have substituted x equals to 2, which is the last part that I'm going to close with when coming to this lesson. We actually substitute, right? We only substitute if that function is continuous at that point. So here we can substitute, so in other words, let me just put a bullet point here. The graph y is equals to x squared is continuous, right, at x equals to 2. So the concept of continuity, or when we say that a function is continuous at a point, it means if you're plotting that graph, it means then that, you know, you don't actually, there is nowhere where you lift the pen. Like, the graph is continuous, it just goes. Like, for example, if we have y is equals to x squared, at the point 2 we are like there is continuity there, like the line is solid. In other words, there is no jump or there is no gap. Like if think of me as a particle, I'm walking on this graph. If a particle is going through, if this is the trajectory of a particle, when it gets to x equals to 2, the graph will still continue. I mean, the particle will still continue on the path. It's not like it will stop or it will jump and stuff like that. So continuity, or a continuous or the continuity of a function, basically what we mean that, okay, let me just put this in yellow. So f of x is continuous at x equals to c. At x equals to c if number one, if f of c exists, right, and the limit as x tends to c of f of x is equals to f of c. So a lot of the functions that were given are actually having this condition. They're actually having the condition that those functions are actually already continuous at that point. So that's why for those functions, it always looks like we are substituting, or we can substitute the point where we want the limit to be. Like for example, with the limit as x tends to 2 of x squared, because x squared is continuous at x equals to 2, then you can substitute x to be equals to 2, which is actually 4. So if the function is continuous at that point, right, then you can actually so if f of x is continuous at x equals to a, then the limit as x tends to a of f of x equals to f of a, right? So maybe the rule of thumb here can be like, if you have any limit, whatever limit that you have, because I think the question is going to be, how do I know if the function is continuous at that point? And how do you know about it is that, in fact, maybe let's put it like this: if you have any limit, I'm saying if you have a limit, right, and then you cannot substitute the limit into it, how can I put it? If when you substitute the limit into that function that you want to find the limit of, if then that function doesn't exist, then it means then that it is not continuous at that point, right? For example, like we have seen that the limit x tends to 0 of 1 over x. Now, when you substitute x equals to 0 here, you have an undefined, or is undefined. Therefore, since 1 over 0, let's do this. Since 1 over 0 squared is undefined, then 1 over x squared is not continuous at x equals to 0. Then when you have a situation like this, then you cannot substitute x equals to 0 into the limit. What you have to do, then you have to check the left limit and the right limit. And then in this case, then it means that you won't be substituting x to be equals to 0, but what you'll be doing is that you'll be substituting values closer to 0, right? So yeah, maybe check the limit first. If when you substitute into into that function. If it's undefined, then it means that that function is not continuous at that point, and then for that you have to substitute values which are closer to x. And then for that you might have to check the left limit and the right limit. You might have to check this. But if when you substitute the limit into that function and it gives you a number which exists, that is f of that number exists, then it means that that function is continuous at that point, and then you can just substitute that. Like for example, like we've seen with the limit as x tends to, let's say, 2 of x squared. If when you substitute so when you substitute x equals to 2 into x squared, you get 4. So if that's the case, then it means x squared is continuous at x equals to 2. Then for that it's just going to be 2 squared, which is 4. Then for this you don't have to take the left limit and the right limit. You can just be like, it is 4. I hope this makes sense, but yep. So I think it's important to know when do you substitute and when do you not substitute. You substitute if, when you substitute, the value exists, which means then that, that function is actually, continuous at that point. And if when you substitute, the function becomes undefined, it means that that function is not continuous at that point. Therefore, you cannot substitute in evaluating that limit. It doesn't necessarily mean that because when you substitute the value is undefined, then the limit doesn't exist. No, the limit can still exist even if when you substitute the point is undefined. And that's the whole core and the whole point of what a limit is exactly that, to say that we are looking at values which are closer and closer to that point. So I just wanted to reiterate this, to say when do we substitute and when do we not substitute, and the reasons behind. I hope this makes more sense. Okay, let's stop it here.